Now, a second property of aromatic compounds, and again, I think this is so cool. You would think, being so full of electron density, these things would like push off of each other really well. Because I mean, think about it, like negative repels negative. So why would two very large sources of electron density actually stick together better than like the alkanes, which rely on dispersion forces? I mean, you'd expect them to push each other off harder, right? Actually, it's the opposite effect. They stick together really well. And this is a weird effect. I shouldn't say weird effect. If you know molecular orbital theory, this makes a ton of sense. So to understand this effect, we have to look at molecular orbital theory. So if we look at the electron density in the aromatic system, it forms, if we hold the ring on its side, two regions of electron density. It looks like a p orbital. And what happens is that when these two benzene rings get close to each other, they act like two p orbitals forming bonds with each other. Their electron densities will overlap and they will create this, like, not really a molecular orbital, let's just call it a supermolecular orbital because it's made along multiple molecules. But basically they stick together because they're kind of forming a bond with each other by overlapping their electron densities. And so because they have this ability to overlap, they have what look like p orbitals interacting to form molecular orbitals that make even bigger molecular orbitals. This is why they have a higher boiling point than something of comparable weight, which is not an aromatic system. So this is another unique property of aromatic systems that we don't generally see with other molecules.